Hello, everyone. My name is Jeff Moran. I'm an assistant professor at George Mason University, and it's my pleasure to present our collaborative work on using titanium dioxide nanoparticles, half-coated in gold, to degrade contaminants in wastewater. I'd like to start by acknowledging my collaborators, especially Young Yuan Ji and Matt Tao, who performed most of the experiments I'll be presenting, as well as Professor Thomas Beecham, who performed the finite element simulations I'll be presenting at the end. So, of course, this is the A+B meeting, and the A in the name of this conference refers to deploying existing technologies at an unprecedented scale to mitigate the effects of climate change in areas as diverse as solar energy, nuclear power, the food-water energy nexus, and water treatment. So I'd like to talk about one particular technology that has significant promise to make an impact in this area of sustainable water treatment particularly, but has not yet been deployed at the scale that it could be. Advanced oxidation processes are broadly a group of water treatment technologies that rely on the production of powerful oxidizing species, most notably hydroxyl radicals, to degrade a wide range of organic pollutants in water. AOPs typically involve a combination of ozone, hydrogen peroxide, ultraviolet light treatment, as well as photocatalysts. And the main reason that there is such interest in AOPs is mainly that they're able to address a wide range of different pollutants, as shown schematically on the right here. Particularly, AOPs are promising to degrade emerging contaminants or contaminants of emerging concern, CECs, which typically are toxic or carcinogenic, but survive conventional water treatments like reverse osmosis or ultraviolet light alone. So one popular method of generating these hydroxyl radicals is to use a heterogeneous photocatalyst. And this is attractive for a number of reasons, including the process is relatively fast. Generally, the AOP generally achieves complete mineralization of the contaminants, meaning that it leaves no toxic sludge behind, and the organic matter is converted completely to CO2 and water. The catalyst is generally unchanged during the process, meaning it can be, in principle, reused in the future. And finally, the catalysts are relatively inexpensive, such as TiO2, and few or even no consumable chemicals, which tend to be expensive, are required. And the figure on the right here shows a number of routes in which the radical species can be generated, either by reaction between photons and photogenerated, or excuse me, reactions between the water and photogenerated holes, or through an intermediate species like peroxide. However, heterogeneous AOPs have a number of challenges that have prevented their implementation in broader water treatment systems. Most notably, the kinetics and thus the energy efficiency are limited by the available surface area of the photocatalyst. And generally, it's difficult to recover these photocatalyst particles from the treated water. Also, the hydroxyl radicals have a very short lifetime. And all of this means that the presentation strategy matters a lot. And for this reason, to maximize the specific surface area, the catalyst is generally presented in nanoparticulate form. There have been a number of studies over the past 15 years or so that have demonstrated the enhancement to this process that can be achieved by decorating the TiO2 with noble metals, usually gold. And generally, the enhancement is typically attributed to surface plasmon resonance, which tends to push the absorption of the TiO2 from the UV, which is the range that matches its band gap, into the visible range of the spectrum, which enables the process to be fueled by visible light, such as that emitted by the sun. But there's been less attention into the exact effect of the ultraviolet light, and particularly the specific wavelength of the light. And interestingly, in the ultraviolet range of the spectrum, another interesting phenomenon occurs with titanium dioxide particles half-coated in gold, creating what are known as Janus particles, named after the two-faced Roman god. They actually self-propel in the presence of UV light. And you can see a video on the bottom left here. This is from Dong and co-workers who initially reported this a few years ago. Whenever the light is on, the particles propel themselves, and whenever it's off, they stop. and the speed increases with intensity. So many people have hypothesized that self-propelled particles, such as these, could actually accelerate the treatment of wastewater in that the particles see more contaminants per unit time, and the increased fluid mixing could potentially increase the mass transfer to the surface. So here, gold Tio2 Janus particles were reported to swim in the presence of near UV light between 330 and 385 nanometers. And the speed also increases as hydrogen peroxide, another common AOP participant, is included. Unfortunately, there's a known limitation with particles that propel themselves in this manner. And that is that as salt is added to the solution, the speed slows down. So here, this is from the original paper from Dong et al. And what you can see is that at 1 millimolar sodium chloride, the speed is noticeably slower than with no salt at all. And at 10 millimolar sodium chloride, the speed is virtually eliminated. That is, the particles just perform pure Brownian motion. This is a known limitation of the self-electrophoresis mechanism that is at play here. I actually have a separate paper devoted to that if anyone is interested. With that in mind, we had the following research questions. First, to what extent do we see enhancement if we just look at ultraviolet light only? So many of the previous studies I showed present a convolution of effects stemming from UV light and from visible light stimulation. So we wanted to look specifically at UV light. Next, how important is the wavelength of the UV light? And then finally, what's the relative importance of each physical mechanism of the enhanced degradation? There's surface plasmon resonance, which generally causes absorption in the visible range. There's self-propulsion, which potentially may enhance mass transfer of pollutant, at least at low salinity. And then finally, enhanced hole electron separation. This is a known effect because of the Schottky barrier that forms between the TiO2 and the gold that causes electrons to travel from the TiO2 to the gold, thus preventing them from recombining with the holes that were photogenerated, which would otherwise be used to generate hydroxyl radicals. So the thought is that enhanced separation of the holes and electrons leads to more hydroxyl radicals and thus faster degradation. We thought to investigate this using Anatase TiO2 particles that were purchased commercially. And you can see here that there's significant polydispersity, but the average size is about 350 nanometers or so. And we coat them with gold using a simple sputter coating process. You can see with energy dispersive X-ray spectroscopy that the gold is indeed coating the particles. And X-ray diffraction confirms that the TiO2 is in the anatase phase, and we do have crystalline gold. Okay, so first we confirmed that the particles do indeed propel themselves. So this is a microscopy video of the particles we studied. And when the UV light is turned on, they do indeed swim. And this again is light in the same wavelength range that was reported by Dong et al. And when the UV light is turned off, they resume simple Brownian motion. Next, let's look at the degradation of 1,4-dioxane as a model of a contaminant of emerging concern. This is a suspected carcinogen that is showing up in the tap water of at least 30 states and has been seen elsewhere as well. First, we looked at 254 nanometer light at a relatively low intensity. And apologies that the legend didn't make it into this panel, but gray refers to just pure control, no light at all. Blue refers to UV light only. White refers to UV light plus TiO2. And yellow refers to all those same conditions, but with the TiO2 half coated in gold. And you can see that there is an improvement at each point. Next, by boosting the UV light intensity by 2 orders of magnitude, we see a dramatic improvement in the performance, especially with the gold TiO2. And note also that this is only over 30 minutes. Finally, by increasing the wavelength to 365 nanometers, keeping the intensity the same, we notice that there is a significantly slower degradation. Okay, so 2 main takeaways here. First is that the wavelength absolutely does matter. And second, unsurprisingly, the degradation is faster in the presence of higher intensity light, particularly in the case of panel B, where the normalized concentration is below 10% after 30 minutes compared to 3 hours at the lower intensity, even with the 254 nanometer light. Next, we looked at the effect of salt and of adding a radical scavenger, namely methanol. So first, if we add salt, and remember, this is enough salt that it should attenuate the self-propulsion entirely, the enhancement is virtually unchanged. So this was interesting because it suggests that self-propulsion, at least in this system, is not essential to observing the significantly enhanced degradation that we see. In fact, it likely doesn't play much of a role at all. At the same time, adding methanol caused a substantial reduction in the degradation rate. And methanol is a radical scavenger, meaning it preferentially reacts with hydroxyl radicals. And what we take away from this data is that in the absence of methanol, it is indeed hydroxyl radicals that are being produced at the TiO2 surface, and it's they who are doing the work of actually degrading the contaminants. Next, we conducted simulations to gain insight into why 254 nanometer light outperforms 365. So this was a finite element simulation in COMSOL multiphysics, solving Maxwell's equations to determine the absorbed energy in each case and in each material. So we simulated Janus particle. We also include a few islands of gold here on the TiO2 face. This simulates the small fragments of gold that you see on the TiO2 face as a natural result of sputter coating. And here we're plotting the absorbance as a function of theta, which is defined in panel B here. In panel C, we're plotting the absorbance in the TiO2 divided by the absorbance in the gold as a function of the incidence angle of the light. Okay, so at 365 nanometers, most of the light is absorbed by the gold, not by the TiO2. At 254, unsurprisingly, most of the light is absorbed in the TiO2, specifically in the case of theta equals 0, when the light is directly incident on the TiO2 face. But generally speaking, for any theta, more light is absorbed in the TiO2 at 254 compared to the gold. Then in panel D, now we're looking at the total light absorbed overall at 254 nanometer divided by the same at 365 nanometer. And again, when we move to 254 nanometers, almost 3 times as much light is absorbed by the TiO2 compared to 365. And indeed, more light is absorbed overall at 254 than at 365. So this gives some insight into why 254 nanometer light generally yields better performance. Finally, we looked at the absorbance within the interior of the particle. And again, the main takeaway here is that in the 254 nanometer case, more light is absorbed near the TiO2 water interface, okay? And conversely, in the 365 case, most of the light at the surface is absorbed by the gold islands, okay? And so again, referring back to the short lifetime of the hydroxyl radicals, you generally want to form them where the light is absorbed, and thus you want to have the light be absorbed near the surface. And we can see that that's happening much more in the 254 nanometer case than 365. At the 365 case, again, most of the light is being absorbed by the gold. In conclusion, the degradation is improved using gold-coated TiO2 particles. 254 nanometer light indeed outperforms 365. Self-propulsion is unlikely to play an important role because it's unchanged in salty conditions. And SPR is unlikely to play a role as well, because again, we're looking only at UV light here, and SPR is generally important in the visible range of the spectrum. Finally, I've listed a few future directions here that will be necessary for scaling this technology up and actually helping to make a difference with sustainable water treatment technologies at scale. We need to compare this with P25 TiO2. This is the industry benchmark for heterogeneous photocatalysis. We need to explore magnetic recollection of the particles, say with a nickel layer incorporated. And we can do optimization. We can develop we need to develop scalable synthesis techniques. That's very important for the scalability of this technology. And finally, testing under solar conditions, since of course the sun emits both in the visible as well as the UV. With that, I'll list the take-home message here and some final acknowledgements. Thank you.